I am audible, Ravi?
Yes, sir. Audible.
Okay. So basically, in our previous lecture, we discussed about Lagrange multiplier. Using Lagrange multiplier, how one can solve the maximize minimize problem. Okay. So in my previous lecture, we discussed about why we need this Lagrange multiplier, because we previously we already know how to solve the maximum minimum problem using Hessian. Okay. Yeah, Kobita, could you please silent your microphone? Yeah, it's fine. Okay. So in our previous lecture, we have seen that what is the use of Lagrange multiplier. Okay. So today also I am going through that motivation. Then we will go for a few more examples. Okay. So in our previous lecture, we solved this problem. Okay. So our question was like that: find the points closest to the origin on the hyperbolic cylinder. This one. So okay, you have to find the point closest to the origin. On where? On the hyperbolic cylinder. Okay. So normal the formula for distance from 0 to 1 point in 3D is this one. Okay. So we are looking for point xyz on the 3D plane, which will minimize the functions f of xyz equal to this one. Okay. Subjected to which condition? Subjected to these conditions. Okay. Is it or not, Ravi?
Yes, sir. Correct, sir.
Yeah, this is the in this condition. So you have to minimize these functions. Okay. Function f of xyz equal to x square plus y square plus z square, subjected to the condition is x square minus z square equal to 1. Okay. So okay. So now, yeah, from these equations, okay, from these equations, this equation, if you eliminate z, what we will get? We will get x square minus 1. Okay. So put this value on the functions f y z. Okay. So after putting the value of z here, we will get two variable functions, g of xy. Okay. So now there is no restrictions, because we already eliminate the function, eliminate the variable z. Okay. After that we are getting that gxy equal to 2x square plus y square minus 1. Okay. Now we know the formula, or know the procedure, know the rules how to find maximum minimum of a two variable functions. So for critical point, we have to, what we have to do? We have to find the partial derivative with respect to x and with respect to y. After that we got xy equal to 0. But if we put x equal to 0 on these conditions, okay, what we are getting? That z square equal to minus 1. But it can't be possible, because this quantity is always non-negative. Okay. So this is not a possible case. So yeah, where we are going for eliminating z variable, that time where our method is not working. Okay. So now we have to go for other elimination. There is two possibility of elimination is there. Two. Okay. One is x, one is z. So at first we try to eliminate the variable z, but anyhow our process is not working. We are getting contradiction. So now we have to go for eliminating the variable x. Okay. So instead of eliminating z, suppose we are eliminate x, what we will get? Yeah, that time we have to minimize these functions, g of yz. Okay, g of yz is nothing but your this one, means you after calculating we will get this one. Okay. Now the critical point, you have to do these things. Yeah, partial derivative with respect to y equal to 0, partial derivative with respect to z is also 0. From there we are getting x equal to y equal to z equal to 0. Okay. Now if you put that value of z equal to 0, what we will get? X is plus minus 1. Okay, so what are the possible critical point? The critical points are this one only. Okay, and if you look, this point is on this surface, x square minus z square equal to 1. Okay, so these are the critical point. Okay, so now we already know how to find the maximum minimum of a two variable functions. Now we have critical points. Okay, and we know that maximum minimum point will be maximum minimum point at the subset, or maximum point is a subset of critical point. So on this critical point we will get maximum or minimum points. Okay, now go for GYY, GYZ, GZZ. Okay, now calculate the Hessian. Hessian is your positive. Okay, so what this conclude, that if your Hessian is positive, then we will go for second derivative. Okay, so
Yes, sir. Then we'll go for second.
sorry,
Yes, sir. When Hessian is positive, we'll go for the next round.
yes, if Hessian is negative, then saddle point. If 0, we conclude anything. If positive, then we have to go for this quantity GYY. This is your also.
And sir, for negative, you said settle point you will get.
Yes.
When Hessian is negative.
Yeah, so
Sir, this settle point, can you please explain us?
sorry.
Sir, this settle point. Yeah. What is this? Sir?
What is the saddle point? Okay, well, I am finishing this one, then I am going to for that one also. Okay,
Okay, sir.
yeah, so already discussed all those things, so for you I will tell you again, no issue. So at first let me finish this one. Okay, yeah, so here we are getting the Hessian is positive and your GYI also is positive. So GYZ, this two variable functions, has a local minimum at the point 0, 0. Okay, it's fine. This function GYZ has a local minima at the point 0, 0. Is fine. Then when we look for our main function f, this is fully depend on your GYZ. Okay. Sorry. Okay, how f of xy is depend on GYZ? Yeah, in such way. Okay, now when we are getting the local minima of GYZ at the point 0, 0, we will get the minima of function f of xyz at the point this one. Okay, is it fine or not? Is it fine, Ravi?
Yes, sir.
Yeah, so what is the value of local minima at the point this one is 1. You can calculate this one, because your f of xy is given by x square plus y square z square. Put the value, we will get 1. So this is the your closest distance from origin. Okay, so this is your answer. Yeah, and this is your required points we done here. But in this whole process we faced one problem. Which problem? When we are going for eliminating z, that time we are facing the problem. But when we are going for the eliminating the variable z, that time this method is work properly. Okay, so we have to avoid. Otherwise, if you have 2 variable, 3 variable, 4 variable, you are going through eliminate one variable, then another variable, then another variable. This is little bit time consuming, na? So it will take time. Okay, so and for math student, you know, if you are not getting proper answer, okay, then sometime we face we are not feeling good. So this process is not not at all good. Okay, then we have to look for another methods. Okay, so next method also some restriction is also there, but next method is better than this one. You can look. Okay, so what is the alternative method? Alternative method is your Lagrange multiplier methods. Okay, so if what is the method and what is the requirement? Our requirement is find the maximum and minimum of a function. Okay, only Lagrange multiplier tell about yeah, only for using Lagrange multiplier we can find, okay, extrema of a function, but using this method we can't give the guarantee of existence of maxima minima. Okay, we can give the existence of maxima minima. Okay, but if you know that maximum minima exists, then this is very easy way to find the maximum and minimum of a function. Okay, subjected to some condition. So what is our requirement? Our requirement is find the extrema of a functions. Okay, this is n variable functions subjected to the conditions. Suppose m condition is there, m restriction is there, g1 g2 up to gm, total m restriction is there. On depend on those restriction, you have to find the extrema of the functions f. No, this is our m. Okay, here we are not telling about existence of extrema or not. Okay, here already we are assuming the extrema exists after some condition, after some constant. We are looking for for the find the extrema of the functions. Okay, what is the method? At first you have to set the auxiliary functions. Set the auxiliary functions. Yeah, f of, okay, so yeah, some mistake is there. Okay, f of x1 x2 xn lambda 1 lambda 2 lambda m. So your f is a function of total n plus m variable is there, x1 x2 up to xn lambda 1 lambda 2 up to lambda n. So your this f is a function of n plus m variable. So set the auxiliary functions is nothing but f, yeah, your this function f plus lambda 1 g1 up to plus lambda m gm. This is your auxiliary functions. Okay, this is the first step. Second step, equate to 0 the partial derivative of f with respect to x1, with respect to x2, up to with respect to xn, with respect to lambda 1 and up to with respect to lambda m. You have to at first find the partial derivative of f with respect to those variable, and after that you have to equate to 0. Okay, then we'll find the value of x1 up to xn lambda 1 up to lambda m, okay, from this equation. Okay, yeah, so from this you have to find the extrema points. So previously I told that this is a definitely good method for finding the extrema of a functions, but this method also some fault. Okay, so what is the fault? Okay, so this theorem is not valid for everywhere. Okay, some restriction is there. This restriction on your constant functions. Okay, so you have to find the extrema of a functions under some condition. Okay, on those conditions, if those condition functions satisfy something, okay, that time we look for the extrema of the given function. Okay, what is the restriction? So your Lagrange multiplier method succeeds under the condition that such extremum value exists where your extremum value have to exist where your gradient of those function are non-zero. Okay, this is the one restriction of this Lagrange multiplier methods. Okay,
So this gradient of gi, I mean the determinant there.
sorry,
So this gradient of gi should be non-zero.
yes,
So this gradient of gi means, I mean del g.
yes, yeah,
Okay,
del g,
okay, so-
yeah, your del g have to be non-zero. Okay, so this is the only one restriction for Lagrange multiplier. Okay, so another remark is there. So using Lagrange multiplier we are getting the possible extremum values, possible extremum points. Okay, so all those extremum points may or may not be the extremum point of f. This is a possible extremum points. Okay, so then how we'll find the what those are the exact extremum points of the functions? Then we have to look the xy points varies over the curve g of xy equal to 0. Okay, okay, Okay. So other condition may be,
Yes, sir.
other condition may be required to determine whether any of such point is an actual maximum minima of f of xy, while your xy is varies over the this functions, this surface, okay, this curve, okay. So in our previous lecture, in our previous example, we faced to difficulty that which variable will eliminate, okay. But I told that Lagrange multiplier is the very comfortable methods for finding maximum minima. That time we don't have to think which variable will eliminate and which one not, okay. So Lagrange multiplier directly tell you the maximum minima if condition is if the maximum minima exists, okay. Okay, so this is your our previous problem. We discussed this previous problem. Your function was this one. We have to minimize this one under the condition, okay, this equal to 0 under this condition, okay. So set the auxiliary equation. Your auxiliary equation is nothing but this one, okay. Then equate f of x equal to 0, f of y equal to 0, f of z equal to 0, f of lambda equal to 0, okay. So after that we got some condition. I am not going for those things, okay. Yeah, so after that we got the required point, this one. So here we did not discuss about which variable will eliminate, which one is not. Here we are directly getting the value, okay. This is the your good things, okay. No, definitely some something we already eliminate from this condition, but this condition is fully depend on your this condition or whatever is given by your statement, okay. So this is here we are not talking about which variable we have to eliminate and which one is not, okay. Here we are directly getting the value of extremum points, okay. So this is your extremum value, okay. Now today we'll discuss about few problems, okay. Yeah. Due to today's tutorial 6, okay, let's try the one problem, okay. I'm writing here. One problem is find the maximum value of three z. You have to find the maximum value of this one, okay, on the curve of intersection of the plane g of x y z equal to x minus y plus z minus 1 equal to 0, and the cylinder yeah. So you have to find the maximum value of this function, okay. What is your condition? So we have to find the maximum value of this one on the curve of intersection of plane and your one cylinder, okay. So where your plane and cylinder will cut on those curve, okay, on that curve you have to find the maximum value of these functions, okay. So we know the methods, okay. Okay, so go for yeah. So what is your auxiliary equation? Auxiliary equation is f of x y z. This is three variable functions, and we have two constant, one g, one is age. Okay, so we need two variable, lambda and mu. Okay, so plus lambda g plus mu h. This is your auxiliary equation. Okay, now you have to go for that first order derivatives, partial derivative all are 0. Okay, setting f of xy, f of fy, f of z equal to f of lambda equal to f of mu equal to 0. We have to do this one. Okay, before that we have to calculate what is this. Okay, so now your x, y, z, lambda, mu equal to your f is x plus 2y plus 3z. Okay, plus lambda into what is your g? G is x minus y plus z minus 1. Yeah, this is your g, x minus y plus z minus 1 equal to 0, this one. Okay, plus mu into x square plus y square minus 1 equal to 0. Okay, x square plus y square minus 1 equal to 0. So this is your auxiliary functions. Okay, now if we do f of x equal to 0, what we will get? F of x equal to 0, we will get here 1, here lambda, here plus 2 mu x equal to 0. Okay, so f of y 2 minus 2 lambda plus 2 mu y equal to 0. Okay, go for f of z 3.
Sir, 2 minus 2 lambda ना मतलब lambda only ना.
Okay, sorry. Yeah, it's fine. Yeah, it's fine. Okay, so f of z is 3 plus lambda, here no z is there. Okay, so this is 0. So from here we are getting lambda equal to minus 3. Okay, yeah, so from here we are getting this one. Okay, now keep it. F of lambda is x minus y plus z minus 1 equal to 0. Okay, x minus y plus z minus 1, okay, equal to 0. Okay, and f of mu is x square plus y square minus 1 equal to 0. Okay, now do one things here. So you have this one. Okay, put lambda equal to minus 3 here. What you will get? You will get mu x equal to 1. Is it or not? Is fine?
Sir, in which equation you have put this?
In 1. So your lambda is minus 3, it is coming minus 2.
Okay.
Minus 2, yeah, it's fine. So okay, and okay, yeah, if you put, yeah, so what about mu? Mu can be 0 or not? Please tell me. Suppose mu is 0. Okay, this is
Sir,
one.
mu
It's
should not be
possible.
0, no?
Yes.
Lambda and mu should be non-zero, no?
Yeah, mu and x also is non-zero, so we are getting x equal to 1 by mu. Okay, yeah, so first one, so put lambda equal to minus 3 here in 2. Okay, so from 2 what we will get? We will get 5. Okay, so y equal to minus 5 by 2 mu. Okay, it's fine. Yeah, so here putting lambda equal to minus 3, so it is 5. Yeah, it's fine. Minus 2 by 2 mu. Okay, sorry, minus 5 by 2 mu. Okay, So this is the value of y, this is the value of x. Now we need the value of lambda, we already got. Okay, yeah, so we need the value of z. Okay, then put the value of x and y here. Okay, what we'll get? If you put the value of x, 1 by mu minus 5 by 2 mu plus z equal to 1. Okay, z is also depend on mu, x y all are depend on mu, so we need the value of mu. So this is, put the value here. Okay, what we will get? This is equation number 5. Okay, 5. So from 5, putting the value of x and y in 5, we get what we are getting. X means your this one, 1 by mu. Okay, put 1 by mu square, y is 5 by 2 mu square equal to 1. Okay, so from here we will get, I'm directly writing the answer, 29 by 4. Okay, you will get, definitely you have to check it. Okay, so then put the value of mu, yeah, x here, here and here. So ultimately what we will get?
Sir, mu square equals to 29 by 4 now.
Yes, it's not coming. Yeah, this one.
Oh, yes, sir, correct.
Yeah, so this is your mu. Okay, so put the value of mu in x, y and z. So I'm directly writing the possible extremum points. Okay, then the possible extreme points are x equal to plus minus, okay, 2 by 29. Okay, y equal to, y will be in opposite. Okay, already one negative was there, so it will be negative positive 5 by 29. Okay, and z is also will be like that, minus plus 7 by 29. Yeah, if you do calculation you will get those points. Okay, it's fine. And all those case you can verify that grad of g is non-zero, grad of is a is non-zero. Okay, you can easily verify it. Okay, so now what is the maximum value of f? So if you calculate, so what are the points? One is 2 root over 29 comma minus 5 by root over 29 comma 1 minus 7 by 29, one pair. Another pair is x negative, y positive and z is 1 plus these things. Two pair is there. Okay, find the value of f, then compare what is the which one is maximum, which one is minimum. So ultimately you will get, so I am writing two pairs here. Two pairs is, one pair is this one, when x is positive y is negative, and corresponding z is 1 minus 7 by 20. This is one pair. Another pair is x is negative, y is, this one is positive and this one is also positive. Okay, put the value this one and this one in your main equations. Okay, here. Okay, and find the value of f. Okay, so yeah, we can easily find the value of f. Your f is x plus 2y plus 3z. Okay, so if you put this one, so what, 2 minus 10. Okay, 2 minus 10 plus 3 into 29 minus
Sir, minus 2.
sorry, yeah, I'm putting this one.
Okay, okay. Sir.
Yeah, at first putting this one on f. So our function is this one. So x is 2 minus 10 plus, yeah, this one. So what we'll get, we are getting minus 31 minus 29 minus 29 plus 3 29 by this one. So ultimately we are getting 3 minus, yeah, this one is getting, and on this point we'll get this one. Okay, at the point of, suppose this take p point, this is q point. So at q functional value will be, okay, 3 plus root 20 root 29. You can check it. So this is your maximum value. Okay, is it fine?
Oh, yes, sir. So, sir, where did we apply Lagrange in this?
Yeah, in full method na. So here this is we set the auxiliary equations. In previously what we are doing, previously we used to eliminate x y z previously. Okay, so now here we are not going for eliminate x y z like that. Here directly we are applying Lagrange multiplier method. This is a first method. First you have to write the auxiliary equation. This is your auxiliary equation. This is the first step. Then you have to go for fx, fy. Your main function is only 3 variables. Okay, f is depend on 3 independent variables, but here we are setting another 2 variable also, total 5 variable. So this is your f. Okay, and this f is depend on your another 2 constants, g and h also. Okay, so this is the method of Lagrange multiplier method, na, this one I already described it. Yeah. So here you already mentioned.
Yes, sir.
Yeah, this is your method. Yeah, this is the method. Okay, so our object was like, you have to find the extrema of the function f subjected to these conditions. So this is our main motivation, and method is you have to set the auxiliary function first. Okay, so suppose your function is n variable functions, you will get one auxiliary function of how many variable will be there. Your function is n variable and m constant is there, then f is a function of n plus m variable. You will get one auxiliary equation. Then go for all, yeah, all required partial derivative. Yeah, you have to calculate all partial derivative. Okay, so suppose f is a n plus m variable, then you have to go for n plus m variable total partial derivative equal to 0. Then you will get the point x1 up to xn and lambda 1 up to lambda m. Then you have to go for the maximum minimum, which are the maximum minimum points of that one. So here we use this formula, is it or not?
Yes, sir.
Yeah, this method we use here. Okay, using this one we are getting the maximum value is maximum value
Sir,
of,
we did not came through finding determinant, no?
no, yeah, this is one. So it did not came through because before describe the Lagrange multiplier method, na, we gave one example that there we was facing problem, which variable we have to eliminate first. Okay, we don't know, na, suppose we first eliminate, in that example we eliminate the variable z1 first, so that time our methods failed. So again we go for eliminating the variable z. So this is the main constant of our previous method. Okay, this is the
Yes, sir.
yeah. So Lagrange multiplier, yeah, here we are not dealing on all those things, eliminating this variable. Okay, here directly we are applying. Okay, is it clear or not, Ravi? Please tell. Ravi?
Yes, sir. Got
Yeah.
it.
So you are looking for determinant type of things. Okay, I am giving one example. yes. Which one is that one? Okay, yeah. So I'm giving one example. So here we will not use the Lagrange multiplier. Okay. So take one. I'm giving one problem. Problem is, okay, you have to decompose a given number. A is given, okay, you have to decompose this A into three parts. Okay, so one number is already given. Definitely this take it as a positive number. Okay, you have to break it into three parts. Okay, to make sure, okay, their product is maximum. This is your problem. Yeah, Ravi, please tell me how we can posit it. So I am giving you one number. Okay, you have to break it into three parts. Make sure that your product should be maximum. Okay, so how you'll break it? What is your
Yes,
guess?
sir. Seems an interesting question, sir.
Yeah, so what is your guess? Please tell me at first. So I am giving you one number 2. Okay, so how you'll break this number in three parts, that your when you will do the product, na, you will get the maximum. Suppose you are breaking like that, x plus y plus z, in such a way that x y z, this product should be the maximum.
Oh, yes, sir. Okay.
Yeah, so what is your normal guess? Suppose this is your one length is there. Okay, you have to divide it into three parts such that your product should be the maximum. Okay, you can do like that. This is your, you take this one and full one, but when you multiply this small number with this one, na, this value will be automatically reduced. Okay, so if you take very small one, them another parts, them after that, but your product will be, in every time product will be reduced. Okay, product will be less. So you have to try to manage it properly. So one guess is there, we can take equal distribute. Okay, otherwise
Oh, yes, sir. Equal.
this is a normal case, na. Suppose this is very small. Okay, after that whatever you will take, your product will be very small. Is it or not? Suppose one is there, one. Okay, if you are taking this one part, okay, another taking 5, another rest of, but when you will multiply with these two number with this one, we are getting, yeah, your product will be very less, na.
Oh, yes, sir. Product will be less.
Yes.
And we have taken very smaller part.
So one guess is that equal distribution. Okay, is it or not?
Oh, yes, equal distribution.
Yeah, this is one normal case. So now we are going for the, yeah, original methods. Okay, them how we can get that equal distribution. Suppose you have to break this number in three parts. Okay, take one part is x, another part is x, now obviously other parts should be like that. Is it? Yeah, someone is want to join. Okay. So our question is, you have to decompose one number a into three parts. Make sure that their product is maximum. Product of that three part is maximum. Okay. So our normal guess is this, your a should be divided into three equal parts. This is normal guess. So how we can get using our known results or known mathematical tools. Okay, so this is the x is, so we are breaking a into three part. One part is x, another part is y. Obvious the rest part is a minus x minus y. Okay, okay, fine.
Sir,
Where
here x equals to y or both may be different?
now we are taking both are different, all are different. No, not all are different. Now we are taking x y are arbitrary. Okay, so it
Okay, sir.
may or may not be equal. We'll go through the maths process. If you are getting equal, then equal. If not get, if are not getting, if you are getting that both are different, then both will be different. We don't know right now, but our guess should be equal. Okay, yeah, because when you are taking very less number, now the full product will be definitely full product will be less. Okay, so now we are going for the normal process. Okay, so definitely since we are dividing one number. Okay, so your x, this quantity may be this one, maybe 0, but it should be either 0 or positive. Okay, okay, and this one is less equal to a. Okay, is it or not?
Yes, sir.
So now, so can we draw one figure in R2 that xy will satisfy these conditions? You have to draw one. Yeah, let's look. Okay, so we are dividing a. Okay, so in three parts, x, y and this quantity. Okay, so your x may be 0, y may be 0. Okay, then this full quantity should be a. Okay, and suppose this two sum is x plus y, this sum is already a. Okay, then your this full quantity should be 0. Okay, so this is maximum upper bound of this x plus y is a. Is it or not? This is a maximum upper bound, na?
Yes, sir.
Yeah, because we are dividing a. Okay, so your x should be on this region, full region. It may be here, maybe here, maybe on this line, or maybe inside. Is it?
Sir, when x plus y equals to a, we will get only two segments. Na?
Other is 0, na? So you can
Okay,
take
okay.
fully, you can take this is a. Okay, okay, you have to divide in three parts. Yeah, one is a, other is 0, other is 0. When x equal to only this one is a, so we are taking a by 2, another is 0. But if you take another is 0, already this full product is 0. Okay, this is definitely meaningless. Is it or not?
Okay, okay, sir.
Yeah. So but x plus x and y can be on the on this line, can be. That time we are getting minimum, this is a different thing. Okay, but x y can be lie on this, yeah, this line. Okay, so this is the your, yeah, main domain. Okay, so now we are so what is our aim? Our aim is what is our aim? You have to find,
We have to maximize, sir, this function.
yes, the function to be maximized is the f of xy is x into y into this number. Okay, and so what is the domain of this function? Nothing, this is only this d. Okay, is it or not?
Yes, sir.
Yeah, so your f is defined on d to r. Okay, this is your function, and we have to maximize these functions. Okay,
Sir, in the second quadrant, it won't take value.
where?
I mean, in the second quadrant, it can't take value, no?
Here you're telling.
Huh?
Yeah, we are not going for negative. We have one
Okay.
positive quantity. We
हाँ
are
ठीक है
trying to
ठीक
divide
Yes.
that one. Okay. So now, so this is your two variable functions. We know the rule how to find the maximum minima. Then go for critical point. For critical point, you have to find the partial derivative with respect to x and partial derivative with respect to y. So your, sorry, this is your f of x equal to 0 means what we are getting, you have to find it here. Okay, f of ei equal to also 0. So please tell me what we will get. So this is your nothing but axy minus x square y minus xy square. Okay, so for x we get ay minus 2xy minus y square. Okay, equal to 0. Here what we will get? Ax minus x square minus 2x. Is it or not?
Yes, sir, correct.
Yeah. So take y from here. A minus 2x minus y 0. Okay, and from here take x. A minus x minus 2y equal to 0. Okay, so from here your y can be 0 or this quantity a minus 2x minus y equal to 0. Okay, here also your x equal to 0 or a minus x minus 2y equal to 0. Okay, is fine.
Yes, sir, fine.
Yeah, so now you have these two equations, try to solve it. Okay, so yeah, multiply this quantity by 2. Okay, and subtract it. Okay, so multiplying this one 2 and subtract it with this one. So a minus 2x minus y equal to 0. This 2a minus 2x minus 4y equal to 0.
A equals to 3y, sir.
A equal to 3y. Okay, so here we are getting y equal to a by 3, and similarly we will get x equal to a by 3. Okay, if you put the value y equal to a by 3, then what will get? This a minus this quantity is 2a by 3, so x is a by 3. Okay, so now total how many possibilities there? One is 0 0. Okay, now if we put y equal to 0 here, what you will get? X is a. Okay, is it or not? Is fine.
Yes, sir.
Yeah, so you have to put this y equal to 0 here, we will get x equal to a. So another possibility is 0a, you will get, similarly you will get a 0 and your a by 3, a by 3. Okay, so you can look that these three are on boundary. Okay,
Yes, sir. These are all convex point, like
yes,
corner point.
corner point. this is your a by 0.
Sir, are these a stationary point also, all these four?
Sorry,
Matlab these all four are a stationary point also? Can,
yeah, this is all a
Stationary.
critical point, na?
okay, so these all four are critical points.
Yes, the four are critical point. Only one is on the interior point. Only one. Okay, a by 3, a by 3. Only one point is on the interior point and 3 are on boundary. Okay. Yeah, my skin is fixed. Oh, okay, now it's
Ah, yes, sir, correct.
and this one is on in your interior point. Okay, interior point.
Sir, definition of interior point, can you once just recall?
Okay, so you graphically I'm telling. Suppose you have this is your R2 plane. Okay, you have this shape. Okay, this is one set. Okay, so when we'll go for interior point, okay, and in R2 your open set is nothing but a disc. Okay, so suppose this is we are telling this is a interior point of that one. That time you have to draw one circle around this one. You have to draw one circle, okay, around that point. That circle have to be containing that set. Suppose this is a set, that circle have to contain the set A. That time we will say this is your interior point. Okay,
Okay, sir. So, sir, which point 0, 0, 0A, why they are not interior?
yeah, because so for you have to here this take this one. Okay, you have to draw one circle. I told previously, draw very, you can draw very small circle, but anyhow this circle can't contain in this domain D. Is it or not?
Ah, yes, sir.
Yeah, so this is the definition, this is the main motivation. So for arbitrary case, suppose R3 it will be sphere. Okay, for R it is your open interval only. Okay, so suppose you have, yeah, this is one line. I am telling this point is interior point. You have to draw one open interval very small. You can draw very small, very big, whatever. Okay, but you have to draw one small interval, open interval. That interval have to be in that set A. For this one,
Okay, sir.
this is
In
not
the
your,
neighborhood of that point.
yeah, this is not your interior point, because if you draw, if you take one hey, what is this? Yeah, if you take one open interval, this open interval can't contain in that set. Okay, so this is the main this is not the main definition, but this is the concept of interior points. Okay,
Sir, a point lying on that straight line will be also not an interior point. On that line,
no,
S plus
this,
Y.
yeah, for this one, na, this is on your R. For R, your open set is interval, open interval. In R2, your open set is one disc. Okay, for this one open set is disc. For this one your open set is only interval, open interval. Okay, and for R3 is, for R3 it is your sphere only. Okay, so this is your sphere only for R3. Okay, yeah, for R3 it is sphere. Okay, so for R3 one point, suppose I am giving one set. Okay, so one point is the interior point of that set. If that point you take one arbitrary small Lopez sphere around that point, that sphere have to contain in that set, then we will say that point is interior. Okay, so this is depend on your in which space the point are lying, which space the set are lying, like that. Okay,
Yes, sir.
clear?
Correct, sir. Yes.
Yeah, so one general definition is there. I am not going for those things. For this is enough for you. For R, open set is open interval. You know, na, interval means take one ray only, bus. Okay, for
Yes,
R,
sir. Got it, sir. Proceed.
yeah, for R2 take open disc, and for R3 take open sphere. Okay, yeah, so these 3 point are not in, or are not the interior point, only this one is our interior point. Okay, Now you can go for the Hessian or all those things. Okay, yeah, you can check for on this point, yeah, check for f of 0 0 what will get, please tell me. Yeah, what will get f of 0 0 if your xy is 0?
We'll get 0, no? It
Yeah,
is in the
your
product.
product should be 0. This one, your function is xy a minus x minus y, this will be 0. If a 0 also 0, 0 is also 0, only this one is there. What will get? A cube by 27, is it or not?
Oh, yes, sir.
Yeah, so this is
Yes,
your
sir. A cube by 27.
yeah, this is your maximum, because all are these all points are critical point. Okay, so these are the possible points of extrema. This is a possible, not outside of those points are not the extremum points. Okay, only these four are the possible points of extrema. Okay, so we are looking for this one is 0, this one is 0, this one is 0. For this one is only positive, we are getting positive value. So this is your the what, this is your the maximum value of, yeah.
Sir, similarly, can we talk about minima also in this case? Or that question will be different?
No, because minimum always 0 na here,
Minimum always.
always 0. So interesting question is only look for the maximum, is it or not?
Okay, sir, got it.
Yes. So this is your required decomposition is like that, a by 3, a by 3, a by 3. This is the required decomposition of a when your product should be the maximum. Okay, now I am giving another interesting problem. Try to solve it. Okay, sorry, this is not a comma. Okay, so you have to determine the maximum value of z equal to x1 product x2 product, this one. Okay, product xn, I am taking after that 1th power of this product x1 x2 up to xn, provided that under condition, provided that this sum x1 plus x2, this sum is a. So you have to find the maximum value of this one. Okay, this is your question. Got it or not?
Oh, yes, sir.
Yeah, so please tell me what will be your procedure for this one. So I want to ask one question. So you have to maximize this quantity. Okay, so if I tell maximizing z is equivalent to maximizing this one, maximizing z is maximizing this function equal to g power n equal to this product only. Is it correct or not? Please tell me. So here z is product of x1 x2 up to xn, then whole power 1 by n, nth. Okay, so 1 by nth power of x1 x2 up to xn, this product. So I am telling that maximizing this z is equivalent to maximizing this function f. F is your g power n. Is it correct or not? Please tell me. Ravi, is this two equivalent? No, n here n is your fixed. N means n variable means fixed. If you can take, you can take 4 5, but your n is fixed here. N is not variable here. Okay, here your n is fixed, only variable is x1 x2 xn. This n variable is there. For the reason we are telling only, if your n is variable, that time, yeah, then we have to think about that. Yes. So now I am now our problem is reduced to, you have to find the maximum of the function f under condition this sum is a. Okay, now tell me what is your procedure. Your f is given and your condition take is g equal to x1. Okay, so you have to maximize this function under this constants. So you already know the Lagrange multiplier methods. Okay, set the auxiliary function. Yeah, so a plus lambda g. Okay, this is the auxiliary functions. What is your f? F is product of this one plus lambda into g. G is plus xn minus a. Okay, now go for partial derivative with respect to I. This is normal, na? There is we don't have to use any theorem for telling this one. Suppose because here we are dealing with only positive number. Okay, take one condition, we are dealing with one positive number. So suppose your n is fixed. Okay, so if your this quantity, suppose f equal to g power n, okay, when this one is maxima, in case of trigonometric function, okay, means you are telling suppose cos x. I think it will be true. I think, okay, I think for this one is also it will be true, because when your suppose this one is at some point, suppose one function is there, yeah, f is there. Okay, f, okay, at the point x naught, this is your maximum. Okay, your f naught is maximum, take m. Okay, so your fs is less equal to m always. Okay, and positive also, we are taking positive. Okay, then this is always, na. Is it or not? Mm, yeah, please tell me. And both are equivalent also. It's fine. Okay, we will check it. Okay. Yeah. So please do this one. Okay. If partial derivative with respect to I, then what we will get? We will get x1 product up to x minus 1. Only that ith component will not be here. Okay. Plus I up to product xn plus here only lambda equal to 0. Okay. Here your lambda can't be 0 because if if lambda is 0 means your this full quantity will be 0. From here we are getting this full quantity is 0. So that time there is no meaning of maximizing or minimizing this function. If 0, then we done, means that is a maximum, that is a minimum, everything for constant function, that is everything. Okay. So we are not looking for the this product is 0, so we have to avoid this lambda equal to 0 also. So take your lambda is non-zero. Okay, is it fine? Now multiply this product by x. Here xi is missing. Okay, so now multiply this product by xi. Then what we will get? Here we will get multiplying by xi. Okay, what we will get? This will get your x1 up to xn, this full product, plus lambda xi equal to 0. Okay, imply x1 product up to xn equal to minus lambda xi. Okay, so this is true for all I. So here we did partial derivative with respect to xi, then after that we are getting this one. Okay, please tell me, is it fine or not? From here what we can conclude, please tell. Can you conclude this one? Please tell. Yeah, so this condition is here. Yeah, so this one is also here. You have to use this one. Okay, x1 plus x2 plus up to xn equal to your a. Okay, no, 1 minute. It's true for all lambda is fine. Yeah, okay. So from here what we are getting, x1 equal to this product by lambda 1. Okay, so for everything we are getting like that, x1 this product by lambda. Okay, and we know this equal to a. Okay, so from what we are getting, Yeah, this quantity all are same, is it or not? Please tell me. All quantity are same, so from here what will get? X equal to a by n, is it or not? Please tell. Is it fine, Ravi? Yeah, so what we are getting? We are getting x equal to a by n. So in this case, what is the value of f is this one, okay? Yeah, so these are a by n. This is the only point of possible of extrema. So at the point the function may have the maxima or may have the minima, okay? So but this is not a minimum point. Our claim is this is the maximum point, because so your f is product of this one. If you take one, x1 is very close to 0, then your full product, what will be your full product? Full product is also is very less, because it will be arbitrarily small if your x1 is very close to 0, is it or not? Lesser and lesser, yes, it's fine. So that time your this quantity your will not be the maximum value of f. Sorry, this quantity is can't be the minimum value of f. So this is the maximum value of f, okay? So this is your maximum value. Then what will be the maximum value of this quantity z? Is a by n, is it or not? Your maximum value of f is a by n power n, then your maximum value of z is a by n, is it or not? Your maximum value of f is this one, okay? Otherwise here, hence your maximum value of z is a by n. It's fine, Ravi? Is it fine? Okay. Okay, so this is your maximum value. Our claiming is this one. So you want to write mathematically this is not a minimum, okay? That time you have to write you can write like directly, like, okay, suppose this value of z, okay, is not minima, okay, because, okay, z can be made arbitrary small by choosing x1 close to 0. Okay, you can write this one is enough, because if you put x1 is 1 by 0 0 0 0 0 like that, okay, definitely your full product have to be very small, is it or not? Yeah, you can write like that, because that time your full product is coming to very arbitrary small, or okay, yeah, so this is your maximum value. Okay, I agree. Sum is in sum is a to product yeah, you can take x1 is like that 1 by a power this one, then we done, I think. Is it or not? Because other quantity na, so at first you have to choose one x1 or arbitrary one component from that product. You have to choose is very small. If you take this type of quantity, then we will done, I think. Is it or not? Please tell. Yeah, so if you have any question from, yeah, from this one can easily observe from this we done already. Okay, so your maximum value of z is a by n. From this one, what we can conclude? We can conclude that do you know what is the arithmetic mean, what is the geometric mean of a positive number? Yes. So this proof is also give the guarantee that geometric mean of n positive number is no more than the arithmetic mean of n positive number. How? Because this is from here we will get what we will get? We will get the arithmetic mean of n positive number, and from this product what we will get? We will get the geometric mean of this product. But this z is your z is less equal to a by n. This is your what? This is your geometric mean of n positive number. Okay, this is your arithmetic mean, and this is equal to your geometric mean. Okay, yeah. So from here your this quantity is your geometric mean. Okay, this quantity is your arithmetic mean. So from this problem also we can observe that geometric mean is less equal to your algebraic mean of n positive number. Is it or not? Ravi, is it clear? Ravi? Through AMGM also we can say, what we can say? We can say z can't be minimum. I could not understand. No, minimum value is 0 here. If you take any one of product is any one of component is 0, means here your full product is 0. So minimum here is minimum value of z is 0 here. Okay, because we are taking all x1, x2, xn all are non-negative. Okay, so here g is product of all the non-negative number, minimum value is 0. Okay, and we are only looking for the maximum value, this one, a by n. Do you have any question, Ravi? Okay, so yeah, so in our next lecture we'll discuss about multiple integral. Okay.